Uh, Good morning. This is Sir C.R. Pradeep from Chennai Visvesvaraya Institute of Technology, Mathematics Department, and I'm here to give a series of 10 lectures on your 18 Math 31, Module 1, which essentially means we are going to learn in my part of the lecture series, you will learn about Laplace transforms, how to find them, some elementary functions, and how to use them, and why should we learn, and what are the applications of them. These are the things which we are going to learn in this series of lectures. So let me start presenting the screen now. So as I said, we are going to learn Laplace transforms, and the syllabus for your course, that is transform calculus, Fourier series, and numerical methods. I'm going to display only that part of the syllabus which I'm going to cover, which is Laplace transform. So definitions and few elementary functions, only statements, and then Laplace transform of periodic functions and a few problems based on it. Essentially, problems means we will try to find Laplace transform of easy combination of these functions. These means the elementary functions. So that's what we'll do. We'll also learn about unit step function. Probably this is the first time you are seeing this. It will be very helpful. It's very useful in engineering. And then we will learn about inverse Laplace transform, how to find inverse of the given Laplace transform. And then, of course, we'll also learn about why we do this. Essentially, we do this because Laplace transforms gives me an algebraic way of solving differential equations. So we will solve a few linear differential equations using Laplace transform. So that was the syllabus, and the objective is, as I have written here, to learn some new techniques to solve differential equations. And Laplace transform is a technique which converts a differential equation to an algebraic one, where the solution is obtained. Normally, solving algebraic equations is simpler than solving the differential equations. And then we come back to the differential setup using inverse Laplace transform to get the solution to the original problem. I know these are a bit abstract, what I just now told you. By the end of this course, we will actually learn how to do all these things. Then it will be clearer. So have patience and be with me. Just one more thing before I start. I have not really met anybody who has understood all of Laplace transform in the very first course. So don't worry. If you don't understand, just plod through a bit. Try to go around, learn a bit this side, that side. Try to understand what's happening. Then you will be able to follow Laplace transforms better. Okay. I would like to start at the very beginning, very elementary things. I want, since you are all in university, you must have already made a transition from numbers to functions. What does it mean? Let me go slow. So, in your very first standard, whenever you entered your school's first time, you are taught numbers. Numbers means we know 1, 2, 3, 4, etc. And then after learning numbers, we started playing around with numbers. Playing means what? When you were playing with numbers, these were the things which you did. You added numbers, you subtracted numbers, you multiplied numbers, you divided numbers. All these are the four fundamental ways in which you played with numbers. Uh, Even then, initially it was numbers meant actually integers. In the sense, you see, everything you see in the example here are all integers. But soon you graduated to decimals and fractions. You realize, oh, there are other numbers other than 1, 2, 3. Like 3.5 minus 2.4 is 1.1. 3 by 2 plus half is 2, etc. These kind of things you learn. You learn to extend your numbers, and then you played around with numbers. Playing around means, again, let me tell you, given two numbers, I know how to do something to that to get a new number or to get an answer. That is something to the two numbers means maybe I'll add or subtract or multiply or divide. Of course, you also learn how to take powers and things like that. By that, you are already in middle school or whatever was over. So you are coming to high school. Then the next kind of questions which were asked was like this: what should be added to 3 to make it 5? Please understand the question. I'm not asking 3 plus 5. I'm asking what should be added to 3 to make it 5. Of course, it's trivial. We have to add 2. How do you know this? Then you are told, there is a method to answer such questions. This is how you do so, known as solving equations. You started with, made this question, what should be added to 3 to make it 5, into a mathematical question. Mathematical question means in symbols you wrote. What did you write? Oh, the whatever number I don't know, I'll call it x. And the question is x plus 3 must be equal to 5. Then they told you there is a way of solving this. You add minus 3 to both sides and then you get x equal to 2. Essentially, this gave rise to what is known as a function. That x plus 3 you see on the right hand side here, left hand side of this equation, is essentially a function. X plus 3 is a function. So basically, while playing around with functions, naturally it gave rise to what is known as a function. So this is an example of a function, x plus 3. I'm sure you have, by the time you finished your class 10, you could give many examples of functions. So how you played with numbers, you also want to play with functions. Even that you have learned in your class 11, 12, for example. So even before we play around with numbers, play around with functions, let me ask you few examples of functions. I'm sure you all can think of what the first function you all think of is a polynomial function. What does it mean? Some of you may not be aware of the name, but don't bother. What it means is something like this: x square minus 2x plus 10. This is an example. You can do billions of such examples of functions. These are all polynomial functions. I won't bother with the definition of polynomial, but you all understand what it means. And then you also learn trigonometric functions like sin x, cos 10x. These are all functions which came naturally in trigonometry, in study of angles, study of various things. You have come across these trigonometric functions. Then you also learned exponential function. This is e power x, or as I written here, 3 times 5 e to the power of minus 5x plus 7. These are all examples of functions. And then I want to play around with functions. Play around with functions means what? Whatever we did to numbers. What did we do to numbers? We added, subtracted. So let's see if we can add and subtract numbers. Add, subtract, multiply, divide functions. This also you already done. For example, here is an example of addition of functions. See, here are two functions. One is x square minus 3, another is x plus 5. I want to add these two. How do I add? Oh, there is a rule. I won't tell you that rule now. But addition of these two will give you x square plus x minus 2. You know how to add functions. Remember, don't think of this as just an expression. It's a function. This is a function. Function means you give me, for example, x plus 5 is a function, means you give me any value of x, I will tell you what is the value of x plus 5. It's like a black box with an input and an output. So this is another black box with an input and an output. If you give me two black boxes with an input and an output, I will give you another black box with an input and an output. And the rules for input and output keeps changing. Here it was x square minus 3, here it is x plus 5, here it is x square plus x minus 2. Of course, you also knew about subtracting functions. Yeah, I won't spend time on this. It's there on your screen. You know how to multiply functions. This is how you multiply functions. Of course, I'm giving you examples of polynomials right now, but I'm sure you can do it for other kinds of functions also. Then you also learn division of functions, where you have to be a bit careful in the sense you didn't want denominator to be 0, and they're a bit subtle. I won't go into details of that. But essentially, you knew how to play around with numbers. The way you knew how to play around with numbers, you also learned how to play around with functions. Right? Essentially, it means adding, subtracting, multiplying, dividing functions. In all this, you see, the main idea is given two functions, I'm combining them in some particular way to get a third function. That is what we are doing. In the first case, two functions given were x squared minus 3 and x plus 5. I combine this to get x squared plus x plus 2. Here, in this example, given two functions where one was 4x power 5, another is 2x cubed, and their quotient is 2x squared. This is a new function. Basically, given two functions, you are trying to construct the third function. You are trying to give a new function. So this is what was meant by playing with functions. But not just this, you learned even more wonderful playing in your class level. That is the next level of playing, which is differentiation. What is this? What do you mean by next level of playing? See, as I said, in all these games, two functions were given to you and you combine them to make one function. In the next level, in class 11 or whenever you learn this, you are given only one function and you are asked to find its derivative. That means this function d, that means this operator d can be thought of as a function on functions. Take a minute to think about it. This operator d is to be thought of as a function on functions. That means if you give me a function here, I will give you another function which happens to be its derivative. For example, if you give me sine x, I'll give you cos x. If you give me tan x, I'll give you secant square x. That's function. You give me one function, I'll modify it and give you another function. That is the next level of playing you saw. And the very first, so this is the notation I use, and please get used to this notation. Capital D of f of x is f dash x. This is a way of coming from one function to another function. And what are the properties we learned all this? First properties of differentiation is algebra of differentiation, which is essentially this. You give me a function, here it is 3x squared plus 10, and give me another function 5x minus 1. When I add these two and then take derivative, this is same as taking derivative of each function separately and then adding. You have to respect this addition. You have to understand this addition and this addition are different. This addition is addition before differentiation, whereas this addition is addition after differentiation. This is something which you need to um, keep in mind. So d of some function f of x plus g of x is equal to d of f of x plus d of g of x. Similarly, this was another property. D of constant times a function, I could pull out the constant times d of the function. So this is another property which you are being taught. I won't go into the proofs of this. I'll assume that you know it, and this has to be, what do you say, must be part of you whenever you see differentiation. So in general, you must have seen such expressions. D of f of x plus g of x is equal to d of f of x plus d of g of x, and also d of a times f of x is equal to a times d of f of x. When when d satisfies these two properties, the English word for this is, we say differentiation is said to be a linear transformation. I won't go into geometry or explanation why it is called linear, but take it as a definition of linearity. That means I'll say differentiation is linear because it satisfies this property. What is the property? D of a times f of x plus b times g of x is a times d of f of x plus b times d of g of x. How many other times I repeat it, I am not under-emphasizing this. Rather, I am not overemphasizing this. This is a very important property. D of a of f of x plus b of g of x is a times d of f of x plus b times d of g of x. You learn many properties of differentiation, but this is the most important and relevant for this course. So whenever somebody talks about differentiation, please keep this in mind. This is called linear transformation because it satisfies this property which you see in the last line of your slide. And then similarly, in your class 12, you learned about integration. Integration also, I of f of x is like a playing with the function. You give me one function, I'll give you another function with some rule. So I of f of x is integral of f of x. Of course, there is a lot of issues here in the sense of concept of integration, limits of integration, all these things are there. I won't go into details of that, I'm sure you know it, but I'll go straight to what is relevant to my course here. An interesting integral is the following. I of f of t is integral of f of t 0 to s, integral of f of t dt. I'm sure you all understand the notations here. I quietly change the independent variable from x to t. That's okay, I can afford to do that. Integral of f of t is, I of f of t is integral of f of t dt from 0 to s. That means you integrate f of t with respect to t and limits are between 0 and s. Suddenly some very magical things happen. So let us observe that. Let us take an example and understand. Take ft equal to t. You take ft equal to t, then I of ft is integral t dt from 0 to s. Integral t dt is, as you know, is t square by 2 between the limits 0 to s. So when I substitute t equal to s, I get s square by 2, and when I substitute t equal to 0, I get 0. So I of ft is s square by 2. Please note this. I of ft is s square by 2. The thing which is not very, one is not very comfortable with is, you see, I of ft, I is an operator which takes a function whose independent variable is t, but the output is a function whose independent variable is s. What is s? You never asked me. S can be anything, I don't care. S is any number, any positive number, because I want integration from 0 to s. Because it can be negative also, it doesn't matter, but for my course, I'll take this to be positive. The s can be 3.5, for example. If s is 3.5, then I have to put 0, I integrate ft equal to t between 0 and 3.5. You can take s equal to 10, I don't care. Then I take integral of t dt from 0 to 10. So this s is the independent variable now in this resulting of integrating of t and limits between 0 and s. So what I want to emphasize is, when the input is ft, that means it's a function of t, output is function of s. Please observe very carefully that t and s are not related. Nobody told, I never told what are the, there is no relation between s and t. Please keep this in mind. What I want to emphasize is, when the input is a function in t, output is a function in s. Output means I is like to be thought of as a function which changes the function to give another function. Think over these lines. So that's what I written here. Observe that the result is a function of s. Okay. So also this integration is a linear transformation. As before, it means I of f of x plus g of x is I of f of x plus I of g of x. This you know, it follows straight from the definition. And I of a times f of x is a times I of f of x. You have used these properties very heavily in your class 11, 12, or even in your first year BE. In general, this is what it means. I of a times f of x plus b times g of x is a times I of f of x plus b times I of g of x. So this is what is meant by saying integration is a linear transformation. Now what I want to do is, I want to define a very similar, this is a integral is a linear transformation. I hope you understand the language. We are seeing two linear transformations till now. One is differentiation, another is integration as defined here. Here means this I of ft is integral of ft dt from 0 to s. This is another linear transformation on functions. That means you give me two functions ft gt. I of ft plus gt is I of ft plus I of gt. Similarly, I of a times ft is a times I of ft, where a is a constant, some number. This much everybody is clear, I am sure. So integration is also a linear transformation. Similarly, D is also a linear transformation. That means you can, instead of I here, you can write capital D. The same formula goes through. D of a times f of x plus b times d of x is equal to a times d of f of x plus b times d of g of x. I know I have shown you for I, but same thing is true for D also. Now what I want to do is, I want to define more transforms which are linear. Because right now I can, I want to define more transforms. Means with more ways of taking functions to functions which are linear. There are many more like this. In this course, I want to study one more such transform, which is called Laplace transform. Definition is here, right on your screen. Laplace transform of a real function ft is defined as L of ft. Please note the notation. Previously, I used to write it. I have defined d of ft, L of I of ft. Similarly, I want to define L of ft, which is integral of now not just ft dt, but e power minus st ft dt. And since integration is with respect to t, I want to write the integral limits is from 0 to infinity. That means here t equal to 0 to infinity. Please understand this. Even though I have not mentioned anything about t being from 0 to infinity, it is clear I am integrating with respect to t because I have written dt. So moment I write dt, you know I am integrating with respect to t and not with respect to s. That's a notation. And now with respect to t, so the limits of the integration is t equal to 0 to t equal to infinity. That's what this is. So L of ft is defined as e power minus st ft dt from 0 to infinity. I won't have time and energy to tell you sort of physical significance of this, but I recommend you to go home, check on your any of your what is it called apps or anything which calculates function, which graphs function, graphing calculators. So try to see how does e power minus st look like, where s is the variable, e power minus st. How does it look? Uh, Please try to see that. You just first see e power minus t only. Forget about put s equal to 1, doesn't matter. E power minus t, how does the function look like? You draw the graph of it once and see. It's not very relevant for your course here, but it gives you a better understanding if you can graph these functions. Then try to take ft to be some simple function and try to multiply these two and see how the graph looks like. These days graphing is very easy because all you have to do is to type this function in your input in the graphing calculator and you will see the graph of it. I'll show you some of this later. And there are some standard notation. These are all from engineering background. So I will, since this is a course for engineers, I will use these same engineering notations. Uh, T is normally denoted as time because ft is a function of time, which means this is evolving in time. That means at different times I have different values for f of t. So it's called time domain. And then here is a small technical thing. Don't bother too much if you don't understand, but just keep this in mind. You see, when I write e power minus st, I want this to be a number. Whatever e to the power of something should be a number. Means I cannot write e to the power of 5 newtons or e to the power of 5 meters per second, or I can't have a units for that. This must be constant. Since t stands for time domain, st must be constant, which means s must be dimensionless. Sorry, st must be dimensionless. St must be dimensionless means s must have dimensions of 1 by t, which means its frequency. So that is why this is called frequency domain. If you didn't understand everything I told, don't bother. It's a standard notation. T is time domain, S is frequency domain. So we say Laplace transform converts a function in time domain to a function in S domain. Please note these things. Observe that f depends on t, whereas its Laplace transform depends on s. Please note this. F in here, f is a function of t. T is the independent variable. Whereas the answer here, e power minus st ft dt. That means you integrate ft with respect to t. So you'll get some expression in s and t. But there you will put t equal to infinity and t equal to 0. So t is become gone. It's vanished. It's no, I can't see t in the final expression. But I'll see s, which means right hand side is a function of s. Like what happened in the case of integral. Similar, very similar thing. I of ft became a function of s. Here also L of ft will become a function of s. And to emphasize this, that you see the Laplace transform of the function f of t is is a function whose independent variable is s. To emphasize this, we use this notation. L of ft is capital F of S. All through my lecture, I will keep using this notation. Small f stands for function of t, capital F stands for function of S, and capital F is precisely defined by this, Laplace of ft. So I could write small g and then I'll write capital G. If I write small h, I'll write capital H here. That means these small and capital are related to f. This is a notation, that's all. And also, I hope this is clear. This is the notation basically. L of ft, I'll call it capital F of f. So whenever I write, even if I don't mention capital F of something, which means, oh, capital F is Laplace of small f. Small f is what I'll tell you in the course of lecture. And also note that this integration is between t equal to 0 to infinity, which means what happens when t is negative is immaterial. Because t negative, it's not even seen in the integration because t is between 0 and infinity. So what happens when t is negative, we don't care, or we don't, I mean, it may function, may be defined, may not be defined, we don't care about it. So these are few things which you need to be familiar with. The definition of Laplace transform, which is, I know it's pretty scary because you look at an expression like this, even if it's a simple thing like ft is sine t, L of ft is e power minus st sine t dt from 0 to infinity. It scares anybody out. How do I do this integration? How do I carry out this integration? How do I find Laplace transform, etc., etc. Don't worry. In your course, you don't have to worry too much about those questions. You have to worry a little bit, but not too much. I will show you what is relevant for you in your course. There are many more things one can tell here, but I will not tell in very general things. These are in general called integral transforms. Instead of e power minus e here, what has happened is ft I'm multiplying by e power minus st and then integrating. Instead of e power minus st, I can put some other function also. Then I'll get an appropriate different kind of integral transform. So the different integral transforms will have different properties. But anyway, don't bother too much about it. This is in general known as integral transforms. This is one example you will see in this course. You will see why I am telling you in this generality. You will see two different integral transforms in this course. This is Laplace transform, and the other one, three in fact, you will see. Another one you will see is Fourier transform. And there is one more discrete analog of this, which is called Z transforms. All these three you will see in this lecture. So try to keep it in mind. Every time what we are doing, start with a function and multiply that function with some other function with some other independent variable. Then integrate this whole thing with respect to the whatever this variable and make this independent variable vanish by giving some limits to it, in this case 0 to infinity. And then resulting, I'll get a function of this new independent variable. That is in general an integral transform. There are a lot of theories of integral transform, which is very interesting and beautiful. Classically, it came about, of course, Laplace was funny. Laplace was not the guy who first used this. It was Euler who used this, but Laplace made it very popular and sort of he used it to solve some very difficult problems. Euler, even though he thought of this transform first, Laplace was the one who actually used it to solve some that day's important problem, like differential equation, some particular differential equation which people didn't know how to solve. He told, hey, this is the method to solve that. So that's why it became famous as Laplace transform. I will tell you this more later. Of course, there's a lot of beautiful things to say about Laplace. I suggest you Google out history of Laplace. Just Laplace as a human being, as a French mathematician. So just go and Google out and see. It's quite interesting. Of course, as I said, this definition scares anybody out. L of ft is integral of e power minus st ft dt from 0 to infinity, and there is no clarity in the usefulness of this definition. Why would anybody want to do this? Nobody knows. I mean, right now we don't know. Once you do this definition, once you uh, understand how to find Laplace transform of various things, I will tell you why we did this. Yeah, I know it's a bit of a you know, I don't know why am I doing, but I have to do it. That kind of thing it is. but I can only tell you that Laplace transform are used to solve differential equations. So that's a good enough aim for an engineer. Engineers come up with lots of different differential equations, and you want to know how to solve it. So Laplace transform is one way of doing this. As I have written here, application of this will become apparent as we study its properties. First, let's go through a few elementary examples. Okay, here are some examples. So let us take this first. Says, so this we have seen already. This is the definition, and this is the example I want to start with. Ft is 1. So this is a constant function. Constant function is 1 all the time. Ft equal to 1, where t is non-negative. It doesn't matter t negative, positive, non-negative, because if t is not negative anyway, I don't care, because after all I'm interested in Laplace transform, where I'm taking integral from 0 to infinity. Anyway, right now I'll take this function which is constant. I suggest, right now I will not do it, but later on I will do it and I will show you also. But before that, you try to graph this function if t equal to 1. How does it look? Take a few minutes. T equal to 0 if t is 1. T equal to 1 if t is 1. T equal to 2 if t equal to 1. T equal to 2.5 if t equal to 1. So if you write t axis on the t value on the x axis, ft is 1. So it's basically a straight line parallel to x axis passing through 0, 1. But I'm interested only t non-negative, so it will be only on the in the first quadrant. I don't bother about what happens in the second quadrant. So that's the function, and I want to find its Laplace transform. By definition, L of ft is capital F of s. Please, I'm writing this because I want this notation to go through your head as quickly as possible. It's very important to understand this notation. L of small ft is capital F of s, which by definition is, what is L of ft? Integral of e power minus st into ft dt, t varying from 0 to infinity. In this particular example, ft is equal to 1. So I'll replace ft by 1. Oh, then it is e power minus st into 1. That e power minus st into 1 is same as e power minus st. E power minus st dt. So you should know how to, so that means I'm integrating with respect to t, and I want to know how to integrate e power minus st. What is it? Before I show the next slide, can you write it down? What is integral of e power minus st? Yes, many of you might have got it. It's correct. E power minus, remember, e power ax, integral of e power ax dx is 1 by a e power ax. So here it's the same thing. A is a constant. Here s is a constant. I know, sir. S, just now you told it's an independent variable. Now I'm saying s is a constant. S is a constant within this integration. That means in this, here I'm integrating with respect to t, so s I can treat it as constant, in the sense s is not dependent on t. S is not really a constant. S is not dependent on t. So integral of e power minus st is e power minus st divided by minus s, and integral limits between t equal to 0 and t equal to infinity. I hope this is clear. It's like integrating e power ax. Integral of e power ax dx is 1 by a e power ax. Here a happens to be minus s. We treat it as constant basically because it is not dependent on t. I'm not telling s is constant. I'm just telling s is not dependent on t, so I can take it out. I can treat it as if it's a constant when I'm integrating with respect to t. So this, you know how to integrate. I mean, you have integrated, you know how to put the limits to t equal to infinity and t equal to 0. When you put t equal to infinity, I'll get minus 1 by s. I'll write it as it is. In the bracket, I'll write e power. If I put t equal to infinity, minus st will become minus infinity. And if I put t equal to 0, it will become e power 0. E power minus infinity minus e power 0. I want s to be positive here. I know these are all small, splitting of hair because of mathematics, which you can't avoid, but we won't spend too much time trying to understand this. You see, what happens is, if s is positive, only then I can write this as minus infinity, because if s is negative, for example, minus 2, then e power minus st will become when t is infinity is very large, and infinity minus something doesn't make sense. So I don't want s to be negative. I'll take s to be positive. If I take s to be positive, e power minus st will be negative because t is anyway non-negative. So this is non-negative. Remember st. So minus st will be for negative. So e power minus st means e power minus infinity will be very small because this will be like 1 by e power infinity. So 1 by e power infinity is 0. And this side is anyway e power 0, so that is 1, no problem. So if you evaluate this, you will get 1 by s. I hope these steps are clear to you. Laplace of f of t when f of t is 1 is, by definition, Laplace of ft is e power minus st ft, but ft is 1. So it's between 0 and infinity. I have to integrate e power minus st, which becomes e power minus st by minus s. I'll keep 1 by minus s outside. Inside I'll put t equal to infinity, I'll get e power minus infinity minus e power 0. I'm putting t equal to infinity once and t equal to 0 in e power minus st. And s I want to be positive. If s is negative, this integral doesn't even make sense. I mean, rather this limit doesn't make sense because e power infinity will become improper kind of thing. This will keep coming regularly in Laplace transform, but we will ignore mostly. If you are mathematics students, I would have spent more time in trying to split hair here, but I will not bother too much about it. The upshot of this is you need to know that Laplace of this constant function 1 is 1 by s. That is the important thing for you. See, here it is. L of, this is how it is written. L of 1 is 1 by s, where s is positive. Why s is positive? I just told you. What if s is negative? S is negative is not even defined. We don't know. We don't care. But I am telling you a new function which is 1 by s, where s is positive. So you can't ask me what if s is negative. S is negative. I'm not telling you anything. It's not defined at all. Anyway, let's not get into arguments on those things. But this is what you need to know. The upshot is that Laplace of a constant of the constant function whose value is 1 everywhere is 1 by s, where s is positive. This is the upshot. Means this is what you need to remember for your examination and to compute various Laplace. This integration is very easy, but in your syllabus it says this proof is not there. I don't know what does it mean, because unless you know this very simple integration, I don't know how you are going to carry out more complicated integrations later. So in any case, I've given you the proof, but nobody will ask you this in the exam. What you need to know is Laplace of constant function which takes value 1 everywhere is 1 by s. Let us try to see some other functions. So this is what I was telling you. T 0 to infinity ht. If you take integral of ht from 0 to infinity, then it may be an improper integral. So to avoid such technical problems, we write 0 to capital T, where capital T tends to infinity, limit of capital T tending to infinity. Let me not bother too much about this hair splitting, but I wanted to be correct, so I included this slide. Let us take another example. Next, I will take purposely exponential function, not trigonometric function. I take exponential function. So let us take this function ft equal to e power at, where a is some constant. Now I want to find Laplace transform of e power at. How to do that? So let us use definition. So definition says capital F of s, which is L of ft, is integral of e power minus st into ft, which is e power at dt, from 0 to infinity. Don't worry, the proof is not there in your syllabus, but I'm just going to explain this. So integral of e power minus st into e power at dt between t equal to 0 and t equal to infinity. I'll rewrite this as e power minus of s minus at. Note, s is not dependent on t and a is of course a constant. So it is like integrating e power minus alpha x dx. So that is nothing but 1 by alpha. Alpha is minus s by a here. E power alpha x. That is e power minus s minus a t between 0 and infinity. Similar to arguments before, you can check when you put s equal to t equal to infinity, this will become 0, and when you put t equal to 0, this will become 1. So 0 minus 1, which is minus 1, and that will get cancelled with this minus, and I'll get 1 by s minus a, and here again s must be greater than a, because if s is less than a, this will be negative, and negative into negative positive, e power t, when t is going to infinity, is undefined, means it's infinity, so we don't want such problems. So we will say we want s to be greater than a. So that means Laplace of e power at is 1 by s minus a. That is what the upshot of this derivation is. Recall, Laplace of e power at is 1 by s minus a. These are things which you need to know very well. Not how to integrate, but the final answer. So instead of going on computing Laplace of different functions, we observe, let us see some general properties of Laplace transform. Let's see if that helps, because this is a boring kind of integration. So let us see. As a first step, one observes, one has to work it out. One observes means it doesn't come by tapas. You have to do it. That Laplace transform is a linear transformation. What does it mean? I have already told you what does a linear transformation mean. For example, what do you mean by D is linear transformation, differentiation of linear transformation? D of f x plus g of x is d of f of x plus d of g of x. And also d of a times f of x is equal to a times d of f of x. Similarly, integration was a linear transformation meant what? I of f of x plus g of x is equal to I of f of x plus I of g of x. And I of a times f of x is a times I of f of x. Similarly, I want to see if L also satisfies this property. That means I want to see if L of f of t plus gt is L of ft plus L of gt. That's very easily verified. Of course, it is true, because L of ft plus gt is I'll multiply f of t plus g of t by e power minus st. But then I can multiply f of t by e power minus st and g of t by e power minus st and then integrate. That is also, these two are same because integration is a linear transformation. So this is true. I won't write the proof, but you must observe this. That's all. L of ft plus gt is L of ft plus L of gt. And also for any constant, L of a times ft is a times L of ft, because just both ways follow from first principle, first definition itself, definition of Laplace transform. So Laplace transform is also what is known as a linear transformation, which means Laplace of AFT plus BGT is A times L of FT plus B times L of GT, where A and B are any constants. Any constants, remember, nothing to do with real number, it can even be complex numbers. In fact, we are going to use that soon. So this is very important property of Laplace transform. That is why I wanted you to look at Laplace transform like playing with functions. For example, differentiation and integration or linear transformation. You are playing with function. I give you one function, you can give me its derivative. I give you one function, you can give me its integration. Integration between some limits and things like that. So they were linear transformations. Similarly, Laplace is also a linear transformation. What does it do? That we will see later. But try to understand that it's a linear transformation. That is sufficient for me. So let us try to find Laplace transform of the trigonometric functions, sine and cosine functions. Again, I'll emphasize this is not in your syllabus, but you must know the answer. You don't have to know the proof. But let me give you a word of advice. If you don't know how to do this, very unlikely you will know how to do other integration, because these are very elementary integration. You must know this. One extra thing you need to know to do this is, there are several ways of doing, but what I am using here is what is known as Euler's formula. You must have used Euler's formula. You must have seen it in your class, whatever, 12 or something like that, or definitely your first year B you have seen. Euler's formula is this, what you see on your screen. E power I theta is cos theta plus I sin theta, where I is square root of -1. It's a complex number. This is a very standard kind of thing. If I start explaining the geometry of this, it will take me far away from what I want to do in this course. So I highly recommend you to go back and look up your class 12 textbook in complex numbers, which tells you this Euler's formula, which is e power I theta is cos theta plus I sin theta. This is what I will use. Okay, in fact, this is the definition of cos and sin actually. So anyway, let me not bother about it. I will just use this formula. Okay, so how do I use that? Here it is. If you put in this formula, if you put theta equal to a times t, because I want t is to be the function, I mean everything I want it to be a function of t. So theta, instead of theta, if I put at, I'll get e power it at, e power iat is cos at plus I sin at. Remember, t is the variable and a is some constant. So then I know Laplace transform is linear, so L of e power iat is L of e power iat is cos at plus I sin at. So Laplace of e power iat is Laplace of cos at plus I sin at, which by linearity says whether you add here or you take Laplace and then add, both are same. L of ft plus gt is L of ft plus L of gt. This means L of cos at plus I sin at is L of cos at plus I L of sin at. Actually, I L of I sin at, but I can pull out because it's a constant. So L of e power iat is cos at plus I L sin at. Somehow, if I can find this and break it up into real and complex part, then this is the real part and this is the complex part. So real part of Laplace of e power iat is L of cos at, and complex part of L of e power iat is L of sin at. I will have found L of cos at and sin at together at one go. So how to do this? Here I am giving you the details. I know previously I already found that L of e power at is 1 by s minus a. We just saw it in this example 2. L of e power at is 1 by s minus a. So L of iat, L of e power iat is 1 by s minus a. Replace a by ia, that's all. I never said a must be a real number. It could be any complex number also is okay. So L of e power iat is 1 by s minus a. I'll rationalize the denominator in the usual way, which is I multiply and divide by s plus ia. Then I'll get this expression s plus ia divided by s square minus s square plus a square, which is I'll break it up into real and complex part. S by s square plus a square plus I times a by s square plus a square. So this means cos 8, this there is a typo here, this must be L of cos 80 plus I sin 80 is L of e power iat, which is equal to s by s square plus a square plus I by s square plus a square. So which means L of cos, in this slide it's written correctly, previous one please make that correction. L of cos 80 plus I L of sin 80 is L of e power iat. That's what we saw in the previous slide. This is equal to s square plus a square plus I times a by s square plus a square on this. So equating real and complex part, I get L of cos 80 is s by s square plus a square. L of sin 80 is a by s square plus a square. These are the two things I get. So these are two very important things for me. I found Laplace transform of two functions at one go, of trigonometric functions. So what all have I found? I have found Laplace of constant function. I have found Laplace of e power at. I have found Laplace of cos 80 and sin 80. Four functions we have found. And also we have seen that Laplace is linear. So we use all these together. There's one more, two more to be done. Let me see how much time do I have. I still have time for doing those. So let me continue. So the next function for which I want to find Laplace transform is hyperbolic functions. Hyperbolic function by definition, many of you may not remember, so I am writing it down here. Cos hyperbolic at is e power at plus e power minus at by 2. And similarly, sin hyperbolic at is e power at plus minus e power minus at by 2. So these are the definitions. Don't ask me why it is so. This is the definition of cos hyperbolic and sin hyperbolic. Now I want to find Laplace of these functions. They are the next functions for which I want to find Laplace transform. These are all elementary functions. That's why I'm trying to find Laplace of all these things. So L of cos h at is L of e power at plus e power minus at by 2. But then by linearity, I can take half out and break up L of e power at plus L of e power minus at. That's precisely what I have done here. L of cos h at is half L of e power at plus L of e power minus at. I know L of e power 80. Just now we found that this is 1 by s minus a. And so L of e power minus 80 is 1 by s minus a, which is s plus a. So you evaluate this, you will get s by s square minus a square. So you must, I mean, there's nothing much to know in this, but it is not in your syllabus. But unless you know these elementary things, there is no way you can solve, find Laplace transform of more complicated functions. So here, what is the upshot? L of cos hyperbolic at is s by s square minus a square. And similarly, L of Laplace of sine hyperbolic at is 1 by s square minus a square. It is written down the details here. You can check. It just follows from definition of Laplace and two properties of Laplace. One is what is Laplace of e power at, and another is Laplace is a linear transformation. So Laplace of cos hat is same as half times Laplace of e power at plus half times Laplace of e power minus at. Both we have evaluated, we have written it down. So you must remember this. Laplace of cos hat is s by s square minus a square. Laplace of sine hyperbolic at is 1 by s square minus a square. Now let us find Laplace of another very important function. You see, normally this is the first function which you would have seen, polynomial function. But here today we started with constant function, and then we went to exponential function, which was the last type of function which we studied actually, because it's easier to do. Polynomial is a bit more tricky. We will do it. Don't worry, we will do it. Then we did. So we have found Laplace transform for constant function, exponential function, so trigonometric functions, and hyperbolic functions. Now we will try to find Laplace transform of a polynomial. So let us take polynomial means I will not bother about general polynomial. I will find for a monomial. Why? Because if I know Laplace transform of t power n, I know what is Laplace transform of 3t power n. How do I know? I will just pull out 3, that's all. I know Laplace transform of t power n plus something 3t to power n minus 1, because if I know L of t power n, I know L of t power n minus 1 also. Then I pull out the constant. So any polynomial can be found if I know Laplace of a monomial t power n. Just this one is required. We use linearity property and we can find Laplace of anyone else, any other polynomial. So how to find Laplace of t power n? Don't worry, it's not in your syllabus, but it's very simple. Laplace of t power n by definition is t power n e power minus st dt. Integration limits from 0 to infinity. But now the problem is, how am I going to integrate this? T power n e power minus st. How have you done this kind of integration prior to this? Do you know how to integrate this? T power n e power minus st. Just think for 1 minute. This you will do by integration by parts. You take first function into second function. Its integral is easy to find. E power minus st integral is minus 1 by s e power minus st. So use that, and I have not written on the details here because it's not in your syllabus, but it's very easy. Just do it, you will get what I have written here. L of t power n is n by s L t power n minus 1. This is the sort of recurrence relation. If I know Laplace of t power n, I can find Laplace of t power n minus 1. Or if I know Laplace of t power n minus 1, I can find Laplace of t power n. All I have to do is multiply by n by s. That's what I have to do. So now I can continue carrying out this repeatedly. If I know L of, for example, what it means is, if I know L of t power, if I want to know L of t power 10, I first need to know L of t power 9. If I want to know L of t power 9, I need to know L of t power 8. If I want to know L of t power 8, I need to know L of t power 7. Like this, I'll keep on coming down. If I want to know L of t cube, I need to know L of t square. If I want to know L of t square, I need to know L of t. If I want to know L of t, I need to know L of 1. But L of 1 I already found it. So I know L of t. You put n equal to 1 in this, you will get L of t is equal to 1 by s into L of t to the power of 1 minus 1, which is 0, which is 1. Means t power 0 is 1. So L of 1 I have found it already, 1 by s. So I'll get 1 by s square. as L of t. I hope this process is clear. This is very important for me. From once I know L of t, I know L of t square. How do I know? L of t square is 2 divided by s into L of 2 minus 1, which is 1. So which is L of t. L of t I just know from 1 by n square. So it is 2 by s into 1 by s, which is 2 by s square. Answer L of t square. Like that you keep on doing for all t power n. You repeat it n times, and L of 1 I know is 1 by s, so we get L of t power n is n factorial divided by s to the power of n plus 1. Uh, n factorial, you know it is n into n minus 1, etc., etc., because I'll keep getting these terms continuously. Once in your life, you must carry out this repeated integration, or repeatedly apply this formula to find, say, L of t power 5. You try to do it, then you will understand this formula. If you don't want to do it, just remember this formula. L of t power n is n factorial divided by s to the power of n plus 1. So in our course, in this course, we are not interested in finding Laplace transform of more elementary functions, lots of things. We won't do it. Instead of that, we will use what is known as table of Laplace transform. It's like table of logarithms. You have table of logarithms. You give me a number, and there is a table which tells me what that logarithm is. Similarly, there is a table. You give me a function, it will tell you what is the Laplace of that. So there are plenty of them. You just type Laplace transform, table of Laplace transform. You will see that this will be table of Laplace transforms available on the internet several places. I have chosen this particular one. Means it's there in your. Let me check if it goes to local. But you can go and check. This is the website. But in any case, even if you don't, for your course, this is the Laplace table of Laplace transforms, which is relevant for you. So let me explain how to read this. Just 1 minute. How much time do I have? I have 4 more minutes. Okay. So I think I can explain this. No problem. So table of Laplace transform tells that for this function, this is the Laplace transform. This is ft. This is L of ft, which is denoted as capital F of x. So if ft is 1, Laplace of 1 is 1 by s. Can you understand this? This is ft, this is f of capital F of s. Small ft, capital F of s. That means small ft, it's Laplace. If e power at is there, its Laplace transform. If the function is ft is equal to e power at, its Laplace is 1 by s minus a. That we have seen already. So in for your exam and for your course, you need to understand, remember this table. You don't have to understand, but if you don't understand this, it will be difficult. We have already proved all these things except these two in full detail. This I have done more or less, not in full detail, but whatever I have done, if you understand and if you write it down, you will get the proof. This last one, p power p, I have not done, but that's okay. So let me repeat. Laplace of constant function 1 is 1 by s. Laplace of e power at is 1 by s minus a. Laplace of sin at is a by s square plus a square. Laplace of cos at is s by s square plus a square. Similarly, Laplace of hyperbolic sine is a by s square minus a square. Laplace of hyperbolic cos is s by s square minus a square. Laplace of t power n, where n is an integer, that means it can be t power 1, t power 2, t power 3, t power 0 also, t power 5, t power 100, t power 1000, t power minus 100 also is possible. Oh, but minus 100 you don't know. How do I do it? So let's not bother. This is not an integer. It's a positive, non-negative integer should be. That's what it should be here. It is n factorial divided by s to the power of n plus 1. There is an extension of this. It says for t power p, where p is any number greater than minus 1. It will not be integer. This is what I was trying to tell. So for example, p can be half. P can be 10.5, P can be 13.2, anything it can be, any of the numbers it can be, it will not be an integer. Then Laplace of t power p is gamma p plus 1 by s p power, s to the power of p plus 1, whereas this is gamma function. So recall, I don't have energy time to recall the definition of gamma function, but I'm sure if you go to your first year textbook or notes, you'll be able to see the definition of gamma function. So you better learn gamma function well and its properties. They are important and relevant for this course. So Laplace, so this is the table of Laplace transformation which you need to remember for your examination. Laplace of these 8 functions you need to remember. Which are the 8 functions? Constant function, exponential function, 2 trigonometric functions, 2 hyperbolic functions, one polynomial with the degree being an integer, and another polynomial where degree is not necessarily integer, it can be any number greater than -1. In that case, this will be the Laplace transform of this. So these are the this is the Laplace table of Laplace transform which you need to remember. Next, I want to show you how I can use this table of Laplace transform to find Laplace of different functions. For example, I want to find Laplace of this. Do I have the time? I think it is time up now, so I will not bother about telling you this. But in my next class onwards, I will tell you how to compute Laplace of this kind of functions. Not very difficult. It follows basically from whatever we have done till now. We put them all together. That's all. Thank you. I'll stop here for today.